What if I told you that in the first fraction of a second after the Big Bang, the universe expanded faster than the speed of light? Not just grew, but inflated by an unimaginable factor. This isn't science fiction. It's a real scientific theory called cosmic inflation. Today, we'll break down what it is, why it's one of the most profound ideas in cosmology, and how it helps us understand our universe better. Hi, and welcome to Stellar Studies, your window to the universe. Now let's dive into cosmic inflation and uncover how this revolutionary idea solves some of the greatest puzzles about the origins of the universe. Chapter 1. The Universe Before Inflation. Let's start with the Big Bang Theory. According to this widely accepted model, the universe began around 13.8 billion years ago as a singularity, an infinitely hot, dense point. From this point, space and time began to expand, cooling over billions of years to form stars, galaxies, and eventually planets. But while the Big Bang Theory explains much about the universe's evolution, it leaves several critical questions unanswered. First, the horizon problem. Why is the universe so uniform? For example, the cosmic microwave background radiation, CMB, the faint glow left over from the Big Bang, has nearly the same temperature everywhere. But if the universe expanded gradually, there wouldn't have been enough time for distant regions to communicate and even out their temperatures. Second, the flatness problem. The universe appears to have a nearly perfect flat geometry. This means that the total energy density of the universe is precisely balanced. But why? Over time, even tiny deviations from flatness should have grown exponentially. Third, the monopole problem. Theoretical physics predicts the existence of magnetic monopoles, single poles of magnetic charge, but we've never observed these. Why not? These unanswered questions suggested something critical was missing from our understanding of the universe's earliest moments. That's where the theory of cosmic inflation comes in. Chapter 2. What is cosmic inflation? Cosmic inflation is the idea that less than a trillionth of a second after the Big Bang, the universe underwent a period of exponential expansion. This phase didn't just make the universe bigger, it stretched space itself at an extraordinary rate. The term inflation was first coined by physicist Alan Guth in 1981, who described it as a period of supercharged expansion, powered by a mysterious energy field. During this phase, the universe expanded by a factor of at least, that's a 1 followed by 26 zeros. To put this into perspective, an area smaller than an atom ballooned to something the size of a galaxy in less than a trillionth of a second. Chapter 3. The Science Behind Inflation. The driving force behind inflation is thought to be a hypothetical scalar field called the inflaton. This field had an associated potential energy, which acted like a reservoir of energy, causing the universe to expand exponentially. As the inflaton field decayed, it released its stored energy, triggering a process called reheating. This created the particles, radiation, and matter that would later form stars, galaxies, and planets. The energy from the inflation also set the stage for the universe's large-scale structure. But inflation didn't just make the universe bigger, it also amplified quantum fluctuations, tiny random variations in the energy field, into macroscopic density differences. These fluctuations became the seeds for the galaxies, stars, and voids we observe today. Chapter 4. Solving Big Problems. So, how does inflation solve the Big Bang's lingering mysteries? First, the horizon problem. Inflation stretched the universe so rapidly that all regions of space were once much closer together, allowing them to equalize their properties. That's why the CMB looks so uniform. Second, the flatness problem. Inflation effectively flattened any initial curvature of the universe, just like inflating a balloon smooths out its surface. Third, the monopole problem. Inflation diluted any exotic particles like magnetic monopoles, spreading them out so much that they became almost undetectable. In short, inflation acts like a cosmic reset button, smoothing out the universe and resolving these long-standing problems. Chapter 5. Observational evidence for inflation. While we can't directly observe inflation, we've found its fingerprints in the cosmic microwave background. The CMB's temperature fluctuations align perfectly with the predictions made by inflationary models. These patterns also explain the distribution of galaxies and clusters in the universe. Another exciting piece of evidence comes from the search for primordial gravitational waves, ripples in space-time created during inflation. While we haven't confirmed their existence yet, their detection would be a groundbreaking validation of inflation theory. Chapter 6: Open Questions and New Frontiers. Despite its successes, there is still much we don't understand about inflation. For example, what exactly is the inflaton field? What triggered inflation and how did it end? Could inflation have occurred multiple times, giving rise to a multiverse? These questions drive cutting-edge research in cosmology. Projects like the James Webb Space Telescope and next-generation gravitational wave detectors aim to uncover more evidence of inflation and its implications for the early universe. Wrapping up, what do you think? Could inflation lead us to the next big discovery about the universe, or even a multiverse? Share your thoughts in the comments below. Until next time, keep looking up, because the universe is always expanding, just like our curiosity. And if this journey sparked your curiosity, don't forget to subscribe to Stellar Studies and join us for more adventures through the cosmos. This is Stellar Studies signing off.